Yes, ma'am, we are live now and we can start.
Okay, okay. So, so let's start. So, I extend a very warm welcome to our first speaker of the day, Dr. Partha Goswami. He has already given quite a few lectures, and he has really, helped the students grasp the concepts of physics. So I welcome all the participants to this 10-week program on learning physics with conceptual and problem-based approach organized by the National Academy of Sciences India, Delhi chapter. So it is my pleasant duty to introduce the speaker to the participants. He is going to give a talk on quantum mechanics today. So Dr. Partha Goswami is MSc, MPhil and PhD from University of Delhi. He is presently an associate professor of physics in Deshbandhu College, University of Delhi. He has done his graduation with first class first position from St. Xavier's College, Ranchi. He has been teaching mathematical physics to BSc Physics honor students for the past 30 years. His area of specialization is condensed matter physics. He has 32 research papers to his credit, mostly under sole authorship, published in prestigious journals of physics. So, Dr. Goswami, you're most welcome, sir. And
Thank
I
you.
request
Thank
you to start your talk and start sharing your presentation.
Yeah, the screen sharing actually will have to be done at your end. I have no way because that is what we have been
Yes,
doing.
yes, sir, we are
Yeah,
So
just a
Varsha,
minute.
do you have his PPT?
Yes, ma'am. Yes, ma'am. Yes, ma'am, we
uh,
have.
Okay, okay, good, good. Then please make
uh,
it full screen. Yeah, she has done it. So,
yeah.
Dr. Goswami, if you are comfortable with your video, you can keep it on. If you're not comfortable, you can also switch it off.
I
And
think there would be some audio problem, so I switch off video now.
no issue, sir, no issue.
Uh,
And
okay.
you will have to tell Varsha when to change the slide.
Yeah, yeah, I will. I will.
Okay, sir, thank you so much. Please start your talk.
Thank you. Thank you. So let's make a beginning. The quantum mechanics is a very non-intuitive kind of branch of physics. Uh, the entire quantum theory can be summarized according to me, in one sentence. It is a description. The quantum physics is description of matter and radiation without the concept of infinitesimally small. To elaborate, in nature, action or changes smaller than h cross equal 1.05 in 10 to the power minus 34 joule seconds are not observed. Such actions smaller than h cross, do not exist. That is the basic tenet of quantum mechanics. This means quantum mechanics introduces a fundamental jitter in every example of motion. This quantum of action, in fact, leads to all the strange, non intuitive observations or behavior we see in the microscopic domain, such as the wave particle duality, tunneling through a potential barrier, uncertainty, indeterminacy relation, or decoherence in quantum computation, randomness in measurement, indistinguishability of quantum particles, quantization of angular momentum and all, tunneling, pair creation, decay, all kinds of bizarre happenings that have been observed are basically due to the fact that quantum mechanics introduces a fundamental jitter in every example of motion. So with this, we would like to come to our basically I am to discuss some problems in quantum mechanics. So I would start with slide number 2. I can see that it is already there in the screen. So suppose we have two functions. I said functions, A and B. And in classical mechanics, I define Poisson bracket of these functions as del A del X del B del P minus del A del P del B del X. X and P are position and momentum. They are the fundamental variables, observables. In classical mechanics, they are just numbers, observables. And the Hamilton's equation, as we all know, we have studied classical mechanics. dx dt is Poisson bracket of position with Hamiltonian. Hamiltonian is kinetic energy plus potential energy, which is equal del H del P. Similarly, dp dt is Poisson bracket of linear momentum with Hamiltonian, which is equal minus del H del X, where X is the position variable. So these are well-known Hamilton's equation, alternative formulation of particle dynamics in classical theory, it applied to any classical problem of classical mechanics, whether we apply Newton's law or we apply Hamilton's equation or we apply Euler-Lagrange equation, we all always arrive at the same result. The only difference is, as I tend to put it, that whereas Newtonian mechanics application, you will have to deal with forces, so you go at the local level. On the other hand, in Hamilton's approach, in Euler-Lagrange approach, you have to deal with energy, which is a kind of global approach. Anyway, now we have another function, say a function q, which is function of x and p. So from the differential calculus, one may write dq dt equal del q del x into del x dx dt, and also del q del p multiplied by dp dt plus del q del t. So if the function q does not depend explicitly on time, del q del t could be ignored. So we have dq dt equal, uh, in fact, if you put in the Hamilton's equation, del q del t in classical terms is Poisson bracket of q as a function of p and the Hamiltonian function. Now, when we make a crossover, switch over to quantum mechanics, the first thing we do is the observables are replaced by operators. What are operators? To give simple example, ddx, ddt, differentiation. This is operator. Why? Because ddx acting on a function x, ddx as such has no meaning, but when it acts on a function x, it will give me the instantaneous rate of change of function with variable x. Similarly, logarithm is an operator. Of this, when acts on a number with a certain base, will give me power or exponent or index. So the basic idea in quantum mechanics is that the observables, the position, momentum, kinetic energy, potential energy, the linear momentum, angular momentum, dipole moment, quadrupole moment, everything would correspond to some operator. They are to act on a certain quantum state, will get me a certain value and the same state back. So operator acting in quantum mechanics, finding or measurement act, a mechanical act, corresponds to, in mathematical terms, action of an operator on a quantum state, yielding certain value, some number, and the state itself. So in yet another mathematical jargon, one may call it, one may say that quantum mechanics basically, quantum mechanical problems basically could be transformed into eigenvalue, eigenvector problems. Eigenvalues are the numbers we get as a result of action of operator on a state, and those states themselves are the eigenstate, are called eigenstate. So it may be clearly noted that the first comes eigenvalue, and corresponding to eigenvalue you have eigenstate, and was a switchover, a crossover to quantum mechanics is ushered in by introduction of the reduced Planck's constant or Planck's constant. So as in this case, in the slide, we can see the quantum, the Poisson bracket QH would be, if replaced by minus I upon H cross, yeah, 1 upon IH cross bracket, square bracket QH, we have made a switch over to quantum domain where observables are no more numbers, they are operators. And this square bracket is called commutator of the two operators Q and H. Q may be position, momentum, kinetic energy, anything, and H is the Hamiltonian. So what we Hamiltonian now is no more function, it is an operator. It is comprising of kinetic energy operator and potential energy operator. Now, with this changed, or with this kind of change, the equation of motion we got in classical mechanics for function q, which was dq dt equal Poisson bracket of q with h, in its quantum mechanical counterpart will be the equation of motion I h cross dq dt equal uh, I h cross dq dt equal commutator of q with h. This is the basic equation of motion which gives me time evolution of an operator acting on a quantum state. So we shall be using this formula now to solve a few problems. Can we go to the third slide now? Okay. We have the simplest system, a free particle in one dimension. Particle is free, no potential energy, no other particle around, no interaction. So Hamiltonian function will be momentum up square upon 2m, matlab kinetic energy, but Hamiltonian operator will be square of the momentum of operator divided by 2m. That is what we have shown. And we wish to show that the expectation value, what is expectation value of px? Px is linear momentum in x direction. Expectation value simply is, like I give an example, like we have in statistics a random variable x, and probability of its occurrence is px. So expectation value of random variable in statistics is given by, it is a discrete case, sigma xpx divided by sigma px. So expectation value in the other case, in statistical statistics case, is sum of the values that one of the values which random variable can assume multiplied by its probability, sorry, sorry, product of one of the values which random variable can assume multiplied by its probability, and then summation over all such terms divided by, of course, sigma px total probability being 1, probability being non-negative proper fraction, the total probability being 1. So expectation value comes out to be sigma x px. In the same line, expectation value of an operator, say px, momentum in x direction, could be defined as uh, operator acting on wave function psi multiplied by complex conjugate of psi. Psi is complex scalar complex function. So multiply by psi star and integrate it over all volume. And in the one-dimensional case, it will be integration over all space x from minus infinity to plus infinity. I repeat, expectation value of xth component of the momentum operator will be xth component of the momentum operator acting on wave functions of the quantum mechanical system under consideration, which in this case is free particle. So its wave function, Hamiltonian being p square upon 2m, wave function will be exponential I kx, where k is wave number, and one is familiar, is 2 pi upon lambda and all that. So one is familiar with that. So anyway, uh, expectation value of uh, xth component of the momentum operator will be momentum operator acting on psi, that is to be multiplied on the left hand side by psi star and then integrated over all values of x from minus infinity to plus infinity. So we wish to show in this problem that for free particle in one dimension, expectation value of momentum does not evolve with time. Whatever expectation value of momentum you had at time t equals 0, at any subsequent time, you will have the same expectation value of the momentum. So to show this, we invoke our equation of motion by which d expectation value of px dt is 1 by I h cross uh, expectation value of commutator of px and h. Now commutator or px and h with a comma within square bracket simply means px into h minus h into px. And one can see easily that h for one dimensional case will be px square upon 2m. So px into h will be px cube upon 2m minus h into px will be also px cube upon 2m, and the 2 will cancel out, will have 0. So expectation value would turn out to be 0. That means the derivative of expectation value of the linear component of the derivative of the expectation value of the x component of the momentum is equal 0, which means expectation value of the x component of the momentum does not change with time. I now wish to show the second problem, that the expectation value of position of there are various representation in quantum mechanics position representation, momentum representation, number representation. We don't go into that. We are presently in position representation. So, in position representation, position operator will simply become C number, will become a number. And momentum operator will be, as you all know, H cross upon I del operator, where del is I del del X plus J del del Y plus K del del Z. Had we had switched over to momentum representation, in that case, momentum would have been a number and position would have been operator minus H cross by I del K. That means derivative within K space. Anyway, we are working here in momentum in position representation. So X hour, though we have put it within conical bracket, but it is understood that X is not an operator, it is a number. So ddt of expectation value of X from our equation of motion will be 1 upon IH cross commutator XH minus HX, expectation value of that, and X being a number, H of course is operator, doesn't matter, number could be multiplied to left or right, commutation commutativity will still be valid. Therefore, what I find is X H. This is X multiplied by Px square. But X, mind you, is of course not an operator. Now, a problem. Problem is I have X, in fact, three operators, A multiply A comma B comma C, A comma B comma C. X Px square basically is actually X comma Px and Px. So A comma BC, A comma BC will be by definition ABC minus BCA. ABC, in that sequence, I can subtract from here minus ACB and add minus, add matlab plus ACB. So in that case, we are getting A comma BC equal A commutator BC plus you have subtracted ACB and added ACB. So you have now what? You have AC commutator multiplied by B. So commutator of A, B, C, A, comma, B, C is equal A, operator A multiplied by BC plus AC plus commutator AC multiplied by B. I think my point is clear to everybody. Is it clear? Is it clear? Hello?
Students, please write in the chat box if it is clear. Yes, sir, it is clear. They are writing.
Okay, very good. So X Px square will be, according to this formula, the commutator of X Px square will be X and what? Px, commutator of X and Px multiplied by Px. Correct? I think I'm clear to everybody. When we apply the formula A commutator BC equal AB, A, ABC plus uh, BAC, and we are taking x square, x px square, we shall get x px commutator into px plus px into another xpx commutator. We shall get xpx commutator multiplied by px plus px and xpx commutator. So we shall get 2 times xpx commutator multiplied by px. Is that clear?
Yes, sir.
Yes, sir.
Okay, very good. So since it is 2 times, so 2 factor will cancel out. And you, I think all of you know the fundamental commutator. X commutator H is I H cross. Do you know that? I H cross. Do you know this fundamental
Yes,
commutator?
sir.
Very good. So put in I H cross. So what are you ultimately left with? You are, after all, after cancellation, etc., you are left with expectation value of px divided by m. But as we have shown earlier, expectation value of px at any time is simply expectation value of px at time t equals 0 divided by m. So we are left with x expectation value of x at any time t is expectation value of px upon m, expectation value of px at time t equals 0 multiplied by t after integration, of course, and integration constant expectation value of x at time t equals 0. Is this calculation? I have written it in short, but I have explained through the use of the formula commutator of A and BC equal commutator of AB into C plus commutator of B into AC. With that formula, when I explain this, I think it is clear to everybody. Next, we go to show that expectation value of uh, delta px is what? Delta px basically is square of the standard deviation. What is it? Square of the standard deviation. uh, I think square of the standard deviation is called variance. So delta px is some kind of variance. So that variance at any time will be the variance of x component of the momentum at time t equals 0. How do I show this? Well, we have ddt of, say, square of the x component of the momentum operator. uh, Expectation value of square of the x component of the momentum operator, ddt of that. The ddt of that will be 1 upon IH cross uh, the commutator of px square and h, expectation value of that, and commutator of px square and h will give me 0 for a free particle. I think all of you agree. Because for a free particle, Hamiltonian is px square upon 2m. 2m, of course, is constant, so can go outside. So you have basically commutator of px square with px square itself, and of course a commutator of any operator with itself will be 0. So you have 0. That means expectation value of px square at time t equals 0 is equal expectation value of px square at any time t. I think I'm clear. Mind you, expectation value of px square is not same as square of the expectation value of px. I think you are getting me. The two things are not same. Okay. Now the standard deviation square delta px at any time t square of that will be, as you all know from statistics, by definition, it will be expectation value of px square minus square of the expectation value of px. The two are different. And just now we have proved that expectation value of px remains constant. So in the left hand side, I for square of the expectation value of px at any time t, I can write square of the expectation value of px at time t equals 0. And the other term, expectation value of px square at any time t, just now we have shown, is also equal expectation value of px square at time t equals 0. So substituting these two values, we are finding that standard deviation or variance or uncertainty in momentum, standard deviation square at any time t will be equal standard deviation square at any time at time t equals 0, which means uncertainty in momentum at time any time t, taking square root of course, uncertainty in momentum at any time t will be equal uncertainty in momentum at time t equal 0. I believe this derivation is clear to everybody. And similarly, one can also calculate uncertainty in position, which of course I have left out for reader to do himself or herself. I go to the fourth slide. Well, I have to prove here that uh, which I'm sure you have seen one very important result through Professor Ghatak is the double slit experiment. Have you seen the double slit experiment? Hello, hello,
Yes, sir.
hello.
Sir,
Yes.
yes.
Okay. Very good. Very good. What is the takeaway from the experiment that we have always to remember that uh, to me the entire result of the double slit experiment could be summed up in few sentences. Suppose I have beam of electron directed onto two slits, and I'm not watching what is happening which electron going through which slit. That means no tracker, no sensor, no detector attached to any of these slits. So electron will show on the screen interference pattern, right? On the other hand, in the same setup, in the slit, if I put in a tracker, a sensor, which will detect uh, which electron has passed through which slit and all that, that means I am making an intervention on a quantum system. And quantum system always, uh, if not being watched, not being measured, always remain in superposition state. A measurement destroys the superposition state and gives a single state, a single wave function. So tracking or putting a tracker on any of these slits or both slits is amounting to an intervention, and that intervention will destroy the interference pattern, and we shall see now only images of the two slits on the screen. So simply put, in very common layman's language put, quantum systems have some kind of inherent unpredictability, not being watched. They are in superposition state. Measurement meaning watching them leads to wave function collapse, superposition state collapse, destruction of superposition, and they reveal only one state. That means quantum states are somewhat, they avoid uh, to show their bizarre kind of behavior. Being in superposition state is a kind of very bizarre kind of behavior. So the system avoids showing that bizarre kind of behavior to prying eyes. And this is what actually your showing your cat experiment also, or paradox also says the same. I don't, everybody must have read Schrodinger cat very thorough with it, so I don't allude to it. So out here in slide 4, what is the relevance of the observation that I have made? The relevance is expectation value of any operator. Operator could be position, momentum. I have seen two fundamental operators till now. And I have, from our calculation just now in slide 3, I have seen if I take time derivative of position or momentum operator, I shall get expectation value of operator B, where for position, operator B will be P by M. That means time derivative of expectation value of position operator will give me expectation value of P divided by M, momentum divided by M. Similarly, if there is, which I have not shown, but could be easily shown, if I have time derivative of momentum, expectation value of momentum operator, this will give me expectation value of antiderivative of potential with distance. Mind you, antiderivative of potential with distance is what? Is force. So what are you finding? You are finding that expectation value of force is equal what? dp dt of expectation value of momentum. Isn't this reminiscent of Newton's second law? Isn't this reminiscent of Newton's second law? Hello?
Yes, sir.
Okay,
Yeah, student are following with you, sir.
okay.
Yeah.
So this is reminiscent of Newton's second law, but with a tag, with a rider. In Newton's second law, there, when you state, there is no such thing as expectation value. Out here in quantum mechanics, you have expectation value of the force equal ddt time derivative of expectation value of momentum. Expectation value you find making measurement, and I have already outlined how you find expectation value. So measurement means intervention. So what you find is that whatever be the particle dynamics law at quantum level, at microscopic level, when you intervene, you get its macroscopic form, which is nothing but Newton's law, which is nothing but Newton's law, which clearly is in line with what I stated regarding double slit experiment. Intervention, our intervention to a quantum system destroys the bizarre feature of quantum system, the superposition state feature. We get very definite, precise, totally deterministic law, which is in this case Newton's law. By the way, here in finding the time derivative, you will need Hamiltonian. So we have put in a general form of Hamiltonian. Say p square upon 2m is the kinetic energy and Vx is the potential energy. And with this, it is easy to show with this equation of motion, it is easy to show our right hand side you have expectation value of force, that means antiderivative of potential with distance, and that is equal ddt of p, expectation value of p, but expectation value of p is itself m times dx expectation value of position. So therefore we get our Newton's law in familiar form. This we shall have to prove. This is called Ehrenfest theorem. So I have proved it here in the fifth uh, slide. Do I think the first part is clear to everybody. I have to prove ddt of expectation of x, expectation of px upon m. We banked upon this equation, which gave me expectation of px upon m. And if I take double derivative d2 dt square expectation of x, that will give me 1 by m ddt of expectation of px. But ddt of expectation of px, I need to show minus dv dx. So I bend upon again the equation of time evolution of the operator, and I had expanded in the third step the potential, which in potential field in which particle is present, to be well behaved, and that means it can be expanded in usual Taylor expansion form, and Taylor expansion always guarantees analyticity. I think all of us know what is analyticity of a function. So we are led to 1 by IH cross sigma n Vn conical bracket, and within that you have the commutator of px and xn, and that upon differentiation will give me Vn nxn minus 1, that is minus dvdx. So this way we have been able to show the result we asked for. I think our students have understood it. Have they?
Yes.
Okay, very good. Then I had other problems as well, like ddt of h, expectation value of h. In quantum mechanics, when you deal with operator, you have to put in expectation value, which I have already defined. So from equation of motion, you get it 0 because expectation, because commutator of operator with itself always is 0. Then I had calculated or showed the counterpart of our law governing rotational motion. We all know what is the angular momentum of a particle. Suppose a particle is there moving with linear momentum p, and from an arbitrarily chosen origin, the position vector of the particle is r. So angular momentum of the particle about the origin is defined as r cross p, and torque, similarly, torque acting on the particle, that too will be a polar vector like your angular momentum. Suppose force acting on the particle is F, and particle is located presently at a point at a position vector r from an origin O, then r cross F is the torque about O. So we wish to show that ddt of angular momentum is torque, say along z direction. I've taken z direction for our convenience. So I think what I need to show is clear to everybody. So this is a bit of calculation, a little lengthy one, but not difficult. We have dl dt equal ddt of x or r cross p. Then I apply product rule, dr dt cross p, x times dp dt. So dr dt is nothing but velocity, and p is also velocity. So you have momentum time, mass times velocity. So cross product of a vector with itself 0, and you are left with x cross dp dt, which is tau. Classically, we know this. Quantum mechanically, I take ddt of zth component of angular momentum. Zth component of angular momentum, I can write down from the formula, L being r cross p. I have written xpy minus y pre-x. So the commutator of Lz and H will have xpy minus ypx, and H, the Hamiltonian, is p square upon v. And I have expanded it, worked out, used the fundamental commutation relation, xp equal ih cross, and ultimately that leads to the expectation value of z, tau z. I think this is too simple. Now we go to seventh slide. Well, we have done quite a few problems of uh, involving the equation of motion of an operator. Now we do some problem where how to find given a wave function. See, if I have a quantum system, I solve for psi, I will get energy eigenvalues and corresponding psi's. So here I am given a fictitious psi for a quantum system. Actually, it is not psi, it is probability density. Probability density is square of the modulus of psi. I think all of you know that. Psi itself is called probability amplitude of the occurrence of an event, and square of the modulus of psi is called probability density, which is psi star psi. I'm sure all of you know this. So probability density of some system, suppose, is x exponential minus x upon lambda, and it is defined over an interval x from 0 to infinity, and you want to find mean, standard deviation, and most probable value. Mind you, expectation value is not most probable value. Expectation value has a different connotation, and you will see that most probable value has a different connotation. So how to find mean? Once again, I invoke my original formula of statistics. If x is a random variable, px is probability distribution, then mean of random variable x will be sigma x px divided by sigma px. Out here, x is a continuous variable, so the summation will be replaced by integration over x from 0 to infinity. So our mean of x will be x px dx integrated from 0 to infinity divided by the px integrated from 0 to infinity. Now px is your probability density, which is actually square of the square of the modulus of the this thing. The probability amplitude psi. So you have put in that px here, x exponential minus x upon lambda, and you, hello, any problem?
No, sir. I guess some student unmuted herself or himself by mistake. Please continue.
Okay, okay. So we have in the numerator integral x square exponential x upon lambda dx, and the denominator exponential minus x upon lambda dx. These are in fact well-known gamma functions. I'm sure students are familiar with gamma function. So we get lambda times gamma 3. Gamma n plus 1 is factorial n. In case of number, of course, gamma is generalization of factorial function. So gamma could be defined for even negative or fraction, etc., etc. You all students all know that. So this is 2 times lambda. So standard deviation square, of course, is x square, mean of x square, or minus square of the mean of x. So mean of x square will be how much? We wrote down x square px dx. It is x cube exponential this, x exponential this, so 6 lambda square. So therefore standard deviation comes out to be square root of lambda. I think it is too simple, clear, should be clear to everybody. So
Yes, sir.
now probability, the most probable value. So for finding that, one needs to differentiate probability density, which I have equated with 0 and found x equal lambda to be solution, and whether it is minimum maximum. To determine that, I have local maximum, minima, local maxima. I have found double derivative. A double derivative yields me at lambda negative quantity. So probability density is maximum at x equal lambda. And this is again a simple problem. Then we have in the ninth slide, we have a free particle Initially, it is with a well-defined momentum P naught, whose wave function is well approximated by a plane wave. At t equals 0, particle is localized in a region between minus a by 2 plus a by 2, and wave function at t equals 0 is a exponential I p naught x by h cross. P naught, naught is here subscript for x between a minus a by 2 plus a by 2 and 0 otherwise. So obtain the normalization constant and then sketch the graph of real imaginary psi and probability density. I have a problem here. Uh, I think all of you have seen what should be the expected feature of wave function. One of the expected features of the wave function is that it should be square integrable. It should be what? Square integrable. That means square of the modulus of the wave function integrated over, had it been minus infinity to plus infinity, wave function for free particle, which is plane wave, as you all know, exponential ikx minus omega t. So that would have been inadmissible in some sense. Reason: square of the modulus of the wave function, and wave function is your exponential I k dot kx if you take. So you get 1. And integrating over minus infinity to plus infinity, which is improper integral, will lead me to infinity. And getting infinity is not square integrability. Square integrability demands that integration over the prescribed limit of square of the modulus of the wave function should be a finite quantity. Fortunately, we have here limits not minus infinity to plus infinity, which would have led to the problem. We have the limit minus a by 2 to plus a by 2. And with the wave function as it is for time t equals 0, which is exponential I p naught x upon h cross, and square of the modulus of that, because exponential, and if you take square of the modulus, exponential function goes away. A could be a complex constant, so you have complex a square dx, and fortunately, your limits are from minus in 8 by 2 to plus a by 2. You get a finite quantity, a modulus, square of the modulus of a. Square integrability is intact. Had this limit been minus infinity to plus infinity, problem would have been not solvable. So this is a total probability. This is total probability, and total probability, as you know from probability theory, is equal 1. As you know from probability theory, total probability has to be 1. So the constant A, which in general should be a complex one, because our the psi is scalar complex. So it could be written as exponential I phi divided by square root of A, where phi is some phase, arbitrary phase. And from now on, we can put phi equals 0. So we have psi x 1 by root A exponential I p naught x upon h cross between minus a by 2 to plus a by 2, and otherwise it is 0. And then I have shown its sketch. in figure 10, uh, exponential I px upon h cross, you apply the Euler formula, exponential I theta cos theta plus I sin theta. So real psi will have that cosine form, imaginary psi will have a sine form, and this third one is the plot of modulus of square of the modulus of psi, which is a square waveform. So, well, these are too simple, so I don't need to really harp on it. Now we go to the concept of Hilbert space. I am sure all of you have studied the vector space. Vector space and how inner product is defined. Inner product is generalization of your uh, dot product for usual three-dimensional Euclidean vectors. So, uh, since you have studied vector space, matrices, etc., because these are very much required for to understand quantum mechanics. So, Hilbert space of any physical system, we associate with any physical system an abstract complex vector space with inner product defined. And inner product, this is known as Hilbert space, right? So, state of the system could be defined by a vector in this space. This is a very good concept. A vector which belongs to this space, a complex vector space with inner product defined, a vector belonging to this space will correspond to state of the system. So following Dirac notation, bracket notation, we usually denote the vectors in this space. Uh, your usual three-dimensional vector spaces you have denoted so far by putting a vector A arrow over at the top of it, vector B arrow at the top of it. So following Dirac here, the vectors belonging to such a space would be denoted by usual bracket notation, vector I. I would call it as vector I, vector J. But mind you, we are not putting arrow or not writing either by in bold letter as is usual practice for denoting uh, usual three-dimensional vectors which we encounter in our everyday physics. So we are denoting it by denoting it by Dirac bracket notation. So quantity inside this conical bracket, if you want to call it, with a bar, whatever you call it, the quantity inside is nothing but a label to specify the state we are referring to. Now, Hilbert space itself could be finite or infinite dimensional, right? Depending on the system to which you are referring to. So dimension D is defined as number of linearly independent vectors we span, and we need to span the vector space. I think this concept of linearly independent vectors you already have seen. Suppose you have a usual three-dimensional vector space, Euclidean vector space, that you require bases. Bases are your unit vectors along three directions, I, j, k, which you may choose to denote in a column vector fashion, because here we shall choose that column vector fashion as denoting the state. So in column vector fashion, vector unit vector I could be column 1 0 0, unit vector j will be column 0 1 0, and unit vector k could be column 0 0 1. So when I write a vector in three-dimensional vector space, I need to have its, and I need to have components along x, y, and z direction, and I need to have the basis. X component of a vector, which is a number, will be multiplied simply with the unit vector along x direction. Similarly, y component multiplied with the unit vector j along y direction, and same with z component. Sum them up, you have representation of vector. So a representation of a vector requires basically then a basis followed by the specification of components. Now, what should basis be? Basis should be linearly independent. IJK matlab column 100, column 010, a linear combination of this will never be equal 001, right? So they are, all three are linearly independent. This choice of 100, 010, 001 is not unique. You can have another choice also for your familiar three-dimensional Euclidean space, but we stick to this simple choice. So they have to be linearly independent, and I need to specify also the components. So uh, suppose we have a complex scalar vector, complex vector space where inner product, which is generalization of product, is defined. What is its dimension? Dimension would be simply the number of linearly independent basis vectors we need to span the vector space. In three-dimensional space, we need three basis vectors. So our dimension of the space is three. So our basis vector we denote by bracket I or vector I, and this has to satisfy orthonormality condition, because after all, states ultimately square of the modulus of psi, as you know, will have to correspond to probability density. So some normalization has to be maintained, and normalization of two distinct states, and they had to be uh, orthogonal as well. To put together, it means the inner product of I and j states basis will be delta ij, where delta ij is Kronecker delta, I equal j delta is 1, I not equal j delta 0. Is orthonormality maintained with our familiar vector space, three-dimensional space? Yes, it is maintained. You can see you have three vectors, 1 0 0, 0 1 0, and 0 0 1. What is the dimension of this matrix? All the three matrices are 3 rows, 1 column, 3 cross 1, 3 cross 1, 3 cross 1, all of them 3 cross 1. So if I demand orthonormality, I said I equal j should give me 1, and I not equal j should give me 0. So take your vector 1 0 0, multiply it by transpose of it, which will be a row vector, 1 0 0 row vector. Is that right? 1 0 0 column vector, to the left of it, you write a row vector 1 0 0. So the two matrices now are conformal for multiplication, because on the left you have 1 cross 3 matrix, and on the right you have 3 cross 1 matrix. So product will be 1 cross 1, that is a single number. Am I clear? So multiply 100 row vector multiplied with 100 column vector will give me equal the product equal 1. I think I am clear to everybody.
Sir, there is a doubt from Krishna Kumar that what
Ah.
is the condition to be Hilbert space finite and infinite?
I will come to that. The Hilbert space could be finite as well as infinite. Of course, if I take a smaller system, I have very few entry, very few states of the system. So in that case, this I'm saying from very off the cuff man in an off the cuff manner. If I have a small system can be in very few states. So the number of linearly independent vectors needed to span the vector space, which will take all these states into account, will be finite, right? Uh, and if I have a very big system, complicated system, which could be in multitude of states, and then number of independent linear vectors needed to span the vector space accommodating all these vectors would be very large. So former would be a finite Hilbert space, and the latter would be a Hilbert space where you have dimension tending towards infinity. Is the answer satisfactory to to your student?
Uh, Krishna, please reply whether you are satisfied with the answer or not. Sir, you please continue. I'll let you know when he replies.
Yeah.
Yeah.
What is essential here is to understand that a small system, what is a small system? A small system without any complication, like a free particle. Well, free particle has its own problem, square integrability problem, etc. I have alluded to. So anyway, I have suppose a small system. Right now, a suitable example is escaping my mind. I have fewer basis vectors needed to span the vector space, which would accommodate all states of that system. Finite. If I have a complicated system, I would need large number of linearly independent factors which would span the complex vector space with inner product defined of, and which will accommodate all the states of the complex system. So such situation would demand a large number of basis vectors. That is infinite, a simple concept. Okay, so with this, we now come back to what I was telling, orthonormality. I had written down the relation ij vector taken their inner product equal delta ij, which is where I and j are basis vectors. Delta ij is called Kronecker delta symbol. I is equal j, then delta is 1, and I not equal j, delta is 0. So to see how I have written it, one can take familiar three-dimensional Euclidean space. 100 is the unit vector along x direction, and transpose of that, because J is all right, I is transposed complex conjugated. So it is transpose of 100, which is a column vector, will be a row vector 100. Row vector has dimension 1 cross 3, column vector has dimension 3 cross 1. They are conformal for multiplication. When I multiply, don't I get 1? Am I clear? Am I clear?
Yes, sir.
Okay. Now, suppose I have our j as 100 and I take as 010, 010, a 010 row vector. So 010 row vector, which is j cap, and 100 is I cap. The two are at right angles. What is the product, matrix product I am getting? 010 with 100. Am I not getting 0? Am I not getting 0? Is it clear or no? Not clear.
Students, please write in the chat box if it is clear or not. Yes, sir. It's clear.
Okay. So you see, the basis vectors have to be orthonormal, meaning inner product of the basis vectors should be, if they are equal, 1. If they are not equal, 0. Not equal 0 is called orthogonality, and if they are equal, 1 is normality. So, or they should be orthonormal apart from being linearly independent. These are some of the requirements to designate a vector space. Now, how to write any state of a quantum system as column vector? Suppose I have two states, psi and lambda. I can always write psi as psi I, which is component, and within bracket I, which is basis vector, and summed over all I. This is how I have been writing. This is a generalization of how I have been writing a vector in familiar three-dimensional space. A vector equal A1I plus A2J plus A3K. This is only a generalization of that. Similarly, I have another state, lambda, which is lambda, which could be written as sum over all i's, lambda I basis vector I. What is this inner product that I have been talking about, which is, I said, generalization of the dot product? Well, the inner product I have denoted by writing lambda psi with lambda uh, inverted, and this is product of lambda I and psi I, but only slight difference. Since lambda is transposed complex conjugated, so you have lambda I conjugated. So you have product of lambda conjugated lambda I, psi I, sum over all I. So our students must appreciate now. Suppose we have two vectors, A, usual three-dimensional, vector B. Vector A is written as A1I, A2J, A3K. Vector B written as B1I, B2J, B3K. Dot product of the two vectors is written as A1A2, A1B1 plus A2B2 plus A3B3. Aren't we just writing just the same thing, but in a slightly elaborate way, in a generalized way? Are these students appreciating it?
Yes, sir. They are writing yes.
Okay. So inner product, how is it defined, is now set. And we always work with orthonormal basis. Orthogonality and normality that there should be satisfied by the basis, at least in quantum mechanics. But in defining, of course, covariant in tensors, covariant, contravariant tensors, you don't require really you require orthogonal bases, but don't require really the magnitude to be unity. Anyway, so that is a different story, which is a non-quantum mechanical matter. And basis set is never unique. You can always go from one basis set to another basis set. And naturally, but vector should remain unchanged, no matter whichever basis set, whichever linearly independent set of states you have stumbled upon, and expressing your vector in terms of that, the vector itself should remain same and the state should remain same. So if you have a different choice of basis set, you naturally will have components different. So our in fact psi, which is our state, could be of a quantum state, which is psi I basis vector I, sum over all I, in fact corresponds to a column vector psi 0, psi 1, psi 2, and so on. I am assuming dimension d. So psi d1 will be the d minus 1 will be the last term, because we started with psi 0, and transpose of it, meaning we have a column vector. This is a row vector, take transpose, you get a column vector. This is what it means. I think I am clear. And wave function we talk about in Schrödinger approach is actually inner product of a kit with position state. A kit psi position state x, uska inner product आप लीजिए, you get psi x. So this is some idea about how to, and then we have these set of problems. Is the time up or what? I think I have exceeded my time limit, haven't I? Hello.
Yes, sir.
So what do you want me to do?
Varsha, has Dr. Sukanto joined?
Not yet, ma'am.
So, sir, please you continue.
No, ma'am. Sir has come just now. Just now
Okay,
he has come. Okay. Yeah.
Yes.
Okay, sir, then it is up to you. If you want to take some questions and wind up, then it is fine with us.
No, problems I will discuss because now 13th slide actually corresponds to, it has a lot of problems, small problems, and solutions are, I have already sent to madam by handwritten solutions. So if that is available with our is it available with you people, the handwritten solutions?
Sir, we
No.
will share them soon.
Okay, okay. In that case, since Dr. Sukanto has come, so let him take over, right? I will then discuss these problems tomorrow.
Good evening, sir. Shukanto this side. You can carry on. It doesn't matter. I can take 1 hour class. No issues.
No problem, Sukanto. It's good to hear you after a long time. I'm sure you have been enjoying your life.